So let's start by solving the quiz again. Now, what does the question ask? What's the minimum work that is needed to be done by the force F? What was the question we've actually, what was the theorem we have sort of proved last time? We said the change in mechanical energy is equal to work done on the object. So clearly, that's what I would want to find out. So what is that change in work? Final energy, final change in energy is final energy minus initial energy, right? And it has two components, our mechanical energy. There is the kinetic energy plus, well, this is the final potential energy minus initial kinetic energy, initial potential energy is work. Now, what's the initial kinetic energy? Initially, it's 0. This is not, it's not moving, so this is 0. So any final kinetic energy the particle will have will just increase the work done, right? So basically, this should be equal to 0 for minimum work. So we basically want this force to cancel gravitation plus the normal force so that it very slowly takes my mass from the bottom to the top. All right? So in part A, there is no friction. So what's my initial energy? Well, it depends. You remember that gravitational energy is always measured with respect to some reference frame. And as long as we are consistent, it doesn't matter what we choose as our reference level, right? So what I'll do is I'll choose my reference level so that my initial potential energy is 0. So initial potential energy is 0. Initial kinetic energy is 0. So my initial energy is 0. Quick question. Can energy be negative? How many of you say no? How many of you say yes? How many of you are sleeping actually? Come on, this is a college class, right? We are in the university. You are supposed to express your opinions here, right? So once again, how many of you think energy can be negative? Okay, almost half of the class. How many of you think it's not possible for energy to be negative? Yes? No, I'm saying, who says I can have minus 5 joules of energy? Who says I can never have minus 5 joules of energy? Okay, the first was correct. I can have minus energy. Why? Because it all depends on my reference level. So just to show you that it doesn't change, it doesn't matter, I'm going to choose my reference level as top. Okay. So now, what's my initial potential energy? My initial potential energy is, if this is H minus mgh, I am H below the reference level. Okay. So let's put in numbers. It's going to be minus 1 kilogram times 10 meters per second square times 1 meter. So it's going to be minus 10 kilogram meter square per second square. We have not talked about units, but I think you know the unit of energy. What's this combination called? Kilogram meter square per second square. It's called a joule. Okay, so my initial energy is minus 10 joules. How about my final energy? Yes, my final kinetic energy is 0. My final potential energy is 0. It's 0. So what's the change in my energy? E final minus E initial. So it's going to be 0 minus 10. It's going to be 10 joules. So what's the work that needs to be done by the force? That 10 joules must be provided by the force F, right? So work needed to be done by the force is 10 joules, as delta E is equal to work. Okay? Now let's do the part B. Part B. And I'll be more conventional now. I'll choose my reference level at the bottom. So now I have F force, but I also have another force. What's the other force acting on my system? Because now I have friction, there is F friction. Okay? Now, what's my initial energy? Initial potential energy plus initial kinetic energy. If I choose my reference level at the bottom of the inclined plane, my initial potential energy is 0. My initial kinetic energy is 0, so this is 0 joules. How about my final energy? Well, I just have H, so my initial energy is, my final potential energy is mgh plus my final kinetic energy is 0 for minimum work. So it's going to be just 10 joules. So delta E has not changed. Delta E is E final minus E initial. So it's 10 joules. But now, when I write delta E is equal to work, that work has two components. There is work done on the object by force F, plus there is work done on the object by friction. So let me show it by work mu. Okay, work done by friction. How can I calculate the work done by friction? Work done by friction, I know that the friction force will be constant here. It will be just kinetic friction, right? So I can actually use F friction dot the total distance that's traveled under that force, right? So what's the D vector? D vector is here. That's my D vector. What's the friction force direction? It's going to be less. What's the amount of friction force? What's the magnitude of friction force? It must be mu times n. N is my normal force. This is mg. So the angle here is theta. So it's going to be mu times mg times cosine theta. Okay. So I'm going to say this is mu mg cosine theta times d, but there is a minus sign. Where does this minus sign come from? Because mu, I'm sorry, the friction force is opposite to the distance traveled, right? D dot mu. What was the dot product? Magnitude of the vectors times cosine of the angle between them. Cosine of 180 degrees is minus 1. What's the question? There's a good question there, I'm sure. You did not understand something. You understood everything? Wow, impressive. So, now, sure.
Why you write like this? We can say that delta E equals to kinetic energy, potential energy, and work done by.
Excellent question. Excellent question. Now, how did we define energy? We said energy is kinetic energy plus all kinds of potential energies, but we spent a good deal of last lecture discussing about what kind of forces can be defined in terms of a potential, right? There were two kinds of forces. conservative forces and non-conservative forces. What was the distinction between a conservative force and a non-conservative force? If I take a object under the action of that force, if I make it go through any path but come back to the same point, if the net work done by that force is 0, then that's a conservative force. Friction is not a force like that. If I take an object, I move it to the left and to the right under friction, there is some energy lost to heat, right? So friction is not a conservative force. It cannot be included as a potential into the energy. All right?
If you write like this, we should.
In this example, you will not lose points. But if I asked the work needed to be done to go up and come back a little bit, then you would see that there's a big difference. Okay? Now, that's a good point. That's the point of the exercise. Friction is not a conservative force. You always have to calculate the work done by friction separately. You cannot derive it from a potential. Let's continue with that. Let's put in the numbers. I don't remember what mu was. Mu is 1 over square root of 3. M was 1. G was 10. Cosine theta is square root of 3 over 2. How about D? If this is 1 meters, D is 2 meters. Excellent. It's as if someone has picked up these numbers to give out nice results. It's minus 10 joules. So delta E was work done by this force plus work done by friction. So 10 is work done by force minus 10. Minimum work the force has to do is 20 joules. Okay? Now, let me make an aside here. Energy we measured in joules, right? The unit of energy is joules. This is a derived unit. In terms of our base units, this is just kilogram meter square per second square. Do you know any other units for energy? Calories. Do you know what's the definition of a calorie? Okay, that's the conversion. What's the definition of the calorie? One centigrade. Okay, so it's the energy needed to increase the temperature of water by 1 centigrade. So, how about, okay, if you buy a chocolate bar, it says 250 calories. What does that, I mean, people who are dieting actually measure calories. What does that mean? Come on, there are so many chemists here. Yes.
Actually, what wrote on written on
Chocolate.
bar is they put chocolate bar in a box and they bomb with they burn with a bomb. Burn has a constant energy that gives. Also, when chocolate burns, it also gives a burn. It also gives energy. This energy difference can tell us how many calories.
So basically, what's written on the chocolate bar is how much energy will be more or less converted to your chemical bonds, the chemical bonds in your body, as a result of digesting that chocolate bar. Okay? So energy concept is all around us. It's a not only mechanical energy, all other forms of energy are important. If you actually go to a, let's say, a thermoelectric generation plant or a hydroelectric dam, there is another different unit for energy. How many of you actually pay an electricity bill? No one pays? Okay, so kilowatt hour. That's another energy. Yes, so but this is again an energy unit, okay? Somewhat unconventional. So let me, and this is kind of strange. So let me define a new concept. Let me define power. Now power is defined as the time derivative of energy. So it turns out the unit for power is obviously the unit for energy divided by seconds. The unit for energy was kilogram meter square per second square. That's divided by a second. It's kilogram meter square per second cube. That's a mouthful again, so we give it a new name. It's called a watt. Okay. Now, who is Watt? Do you know what he did to deserve that distinction, to be called and to be given the name of a unit? You must have done something important. He actually invented the steam engine, more or less. So he actually built the first locomotive working under steam, and he wanted to sell this to a mine operator. Okay, he said, "Hey, you have all these horses, mules, going down into the mine and bringing out the coal. Why don't you do it with my steam engine?" So the mine owner, he said, "You know, you're asking a lot of money for that device. You have to tell me how many horses do the same work. Okay, so what's basically the horse equivalent of your locomotive engine?" So the first unit for power was not watt, it was horsepower. So horsepower, it turns out, is something like 750 watts. So that's, but this whole story has a point. The point is that now we give very distinct mathematical definitions for the concept of power and energy. For example, for kinetic energy, we said it's 1/2 mv square, right? So in our daily usage, sometimes we say, "Hey, I'm very energetic today. I feel I have a lot of energy." With this definition, it means either I have a lot of mass or I'm moving really fast, right? Or we have a lot of potential energy, not the kinetic energy. How about power? Now, here's the thing. What's the derivative of the kinetic energy? What's the power just coming from our kinetic energy? Let's take a derivative of this. Hopefully the mass is constant. It's a constant. I'm taking it outside, like 1/2. d by dt v square. So m/2 2v dv dt. 2's cancel. V times m. What's dv dt? A. What's ma? Force. So F times V. I did this in 1D, but more generally, I could do it in 3D. So the power that's needed to change your kinetic energy is force dot product with your velocity. Again, be careful about your instinctive thought of power. We call many different things power. When we say our rector is a pretty powerful guy, do we mean Abdullah Atalar's force is large or velocity is large? No, we don't mean those things, okay? Be careful about your daily usage of these words. They are not the same thing. I mean, another example, they are not the same thing. We actually mean different things in daily life with power and work. And here is the thing. If I'm actually carrying a very heavy load, if I'm just keeping it there, how much work do I actually do? Well, our definition is pretty clear. The work done to carry any object is F dot D. If I'm not carrying it up or down, that is 0, so it's 0. Does that mean the weightlifters are not doing a lot of work? Well, okay, so they are not doing work to change the potential or kinetic energy of the weight they are lifting. However, it's really interesting. The muscles, animal muscle, the human muscle, is a strange object. It needs constant energy conversion. It actually converts a lot of energy to heat and does chemical reactions inside to be able to apply a force. Okay? So it's just that the machine inside is dissipating energy when you're actually holding something up. Right? So again, you will be very tired if you actually carry 100 kilograms of weight, just even laterally. But all that energy is not going to change the total mechanical energy of the mass you're carrying. It's going to the chemical reactions inside your muscles. All right? So, now, let me remind you one more thing. We're going to solve more examples, but maybe the summary so far. We said the change in energy is work done on an object. We defined the work done in most general case as the line integral of force from the initial point to the final point on any given path. But if I had a constant force, it just reduced to F dot the displacement vector. On the other side of that equation, we said energy has two components. There is kinetic energy plus potential energy. Kinetic energy has only one definition, 1/2 mv squared. However, potential energy can have different sources. All conservative forces can be expressed in terms of a potential. And I said a lot of forces in nature are actually conservative, like the electrostatic forces, like the magnetic forces you're going to study in 102. But here specifically we talked about two examples. We said if I have a spring, the potential energy stored in a spring is 1/2 k times delta x, or we just called it x, I think, x squared for a spring. And we said gravitational potential is m times g times h. H is the height above a reference level. But I'm a little bit bothered by our second definition. Why? Because we derived this for F, the gravitational force on an object, or the weight of that object, being m times g, right? But that was only an approximation. Only an approximation to the real potential energy. The real gravitational potential energy, or the real gravitational force, F gravitation, was g m Earth m over r square, and that r is distance from the center of the Earth. So if I would like to understand the change in potential when I move a pen by 1 meters, obviously the initial formula mgh would be enough. But if I actually want to send a satellite to geosynchronous orbit, that formula should break down. Why? Because I need to actually use the correct gravitational force formula to derive that potential. Okay? So let's actually talk about potential energy for gravitation. Essentially, I'm asking the following question. Let's say this is Earth. Let's do this by an example. This is our Earth. If I drop an object from a distance r, let's drop a meteor from distance r. How fast will it hit the surface of the Earth? That's what I would like to find out. Okay? Is the question clear? I'm designing a new weapon. I'm doing the orbital strike. I drop some object from the orbit, and I'm ignoring all kinds of air friction. How fast will that small mass or big mass hit the Earth? That's what we'd like to try. All right? Well, how do I solve this? Well, I know the following. Let's not define the gravitational potential yet. I have the formula. The change in kinetic energy is work done by all forces, right? Now, what's the force when you are at distance at any point here? What's the force? If you're x away from the center of the Earth, gravitational force on that mass, let's say this mass is small m, is g m Earth divided by x square times m, right? So what's the work done by gravitational force? The work done by gravitational force must be F dot dl from the initial point to final point, right? So this force is, if what's my initial radius? Initial radius is small r, final radius is big R or r Earth, right? dr would be my dr, but I need to write the force. I said g me over x squared times m times dx. That would be my f dot dl. Okay. Now, what's the integral? Integral 1 over x squared dx is minus 1 over x. Good. So this is going to be g, m, e, and small m are constants, minus 1 over x at re and r. So this is going to be g, m, e, m, 1 over small r minus 1 over r earth. Sorry? Yes, so that's the point I'm trying to make. But what is delta kinetic energy? What was my initial kinetic energy? My initial kinetic energy was 0, so let's write it like that. K initial minus K final. This is 0. So this is minus 1/2 m v final square. Now, be very careful. G, m, e, m. 1 over r minus 1 over r earth. Which one?
Why is
No, yeah, okay, good. This should be K final minus K initial, right? So it's going to be 1/2 m square. Now, here's the question. Is this quantity positive or negative? Is small r larger than r earth? So this whole thing is negative. The other side is positive. So we have done something wrong. What did we do wrong here? Okay, so let's be very careful here. I said this is f dot dl. Force and my path are in the same direction, but what I called x is increasing as I go out. My dl is actually in the negative x direction. So starting from there, I should have said this is minus dx. Okay, so I would have a minus sign here, a minus sign here, and a minus sign here. So it all nicely works out. Now 1/2 m v final square, and I'm going to write this in a strange, some kind of strange way. I'll say this minus g m earth m over r earth is equal to minus g m earth. Now, why am I writing it like this? Because I'll say, hey, this is my kinetic energy, final kinetic energy, and I'll call this object with the minus sign as my true gravitational potential energy. So the gravitational potential energy of two objects that are separated by a distance r, u gravitational, is minus g m1 m2 divided by r. So here we come back to our first question. Can potential energy be negative? It turns out for this gravitational potential energy, it's always negative. Okay? So it can be negative. Don't panic. If you find a negative energy, it's allowed. If you find negative kinetic energy, then panic. Then you have done something wrong. Right? 1/2 mv square is always positive. But gravitational potential, it turns out, is negative. Let me quickly ask the reverse question. Let's say I'm on a planet with mass m and our planet, so this is mass planet, and I've landed a small lander, small spaceship on it. Okay. Now, I'll fire my rocket. I'll give this an initial velocity, vi, and I would like to get away from this planet. I want to escape to infinity. So, what should vi be so that the spaceship can escape? And this is called, actually, just as the name, as this question suggests, this is called the escape velocity from any planetary body. Okay. Now, what happens if I actually fire this thing or throw this thing with a escape velocity less than, with a velocity less than the escape velocity? It will go up and it will come back down again, right? So, what do I want? What's my initial energy? Let's find out my initial energy. My initial energy is, the kinetic energy is 1/2 m v escape square. What's the gravitational potential energy? Minus g m planet m divided by r planet. No square, be careful. What's my final energy? Well, I want this object to go to infinity with the minimum possible velocity. So when I reach infinity, sort of my turning point has become infinity. So my final kinetic energy, I want that to be 0. And my final potential energy would be minus g m planet m divided by infinity, which is 0. So my final energy is 0. So essentially, E initial is equal to E final, 1/2 m ve square minus g m planet m divided by r planet is 0. M's cancel. Ve is 2g m planet divided by our planet. Now, this thing is quite big velocity for planetary objects. But for small things like asteroids, it can be quite small. Do you remember last year there was a lander on a comet, the Philae lander landed on a European space mission, right, on a comet. For that comet, apparently the escape velocity was so small, it was, I think, less than 1 meters per second. They were worried that the object may, when it first hits, can be reflected off the surface and then go to infinity. Actually, even on some asteroids, if someday humans land on asteroids, from a lot of asteroids, you can jump off to infinity. You know, you jump and you never come back. That's quite contrary to what we feel on Earth. When we jump up, we always come down to Earth. But if someday you land on I don't know if any of you will land on an asteroid, be careful about your jumps. You can actually go off to infinity. Okay? I'll see you next week.